Hi everyone, my name is Ragim. Thank you for coming to my presentation. Today I'm going to talk about ESP-tool.py, Espressif's Swiss Army knife. So to start, what is ESP-tool.py? It's an utility to communicate with the ROM bootloader in Espressif chips. It's Python-based, it's completely open source, and it's platform independent. In other words, it's a feature-rich set of tools for programming and configuring ESP MCUs. That's why I often call it a Swiss Army knife. You can see the tool is hosted on GitHub. You can open our repository at github.com/espressif/esp-tool. I will be giving my talk from two angles. First, I'm employed by Espressif. I work for IDF Tools team, and we develop open source tools for working with ESP chips. And because of that, we get lots and lots of great feedback from the community. In our GitHub repository, we get issues and pull requests every week. So we get lots and lots of feedback, which is valuable, and we can improve the tools based on it. But second, and I think more important, is that I'm also a user of ESP-tool, and I've been a user for a long time, long before I joined Espressif. Here we can see an ESP device being used in one of my projects, which is LED sign. Okay, overview. What are we going to talk about? First, I'm going to explain how to use ESP-tool.py. Second, how does it work and how to debug issues, because these two are quite related. And last but not least, I will introduce some other tools which come bundled with ESP-tool.py. Let's get into it. So how is ESP-tool.py used? You can use it standalone as a command line tool, but it's also used under the hood of a framework or GUI, such as Arduino or ESP-IDF. So if you've ever used Arduino framework and click the upload button and you've seen a text like this, this is output from ESP-tool.py. So because of this, even if you're not using it directly as a command line tool, I think it's beneficial to know how it works and how to debug some issues, because you might be using it even if you don't know it. How to get started with ESP-tool? ESP-tool.py is hosted as a package on the PyPI index. So if you have Python 3.7 or newer later installed, you can just call pip install ESP-tool. Then you just need to connect an Espressif chip, and then you can run your commands like ESP-tool.py, the command, or Python/m ESP-tool, and your desired command. You don't have to remember all of this. Just visit our documentation, and the installation guide is there for your convenience. So what can ESP-tool do? First, it allows you to get information about the ESP chip you have. So before we continue, let's do a quick demo of what we know so far. Here I'm in my terminal, and I can actually install ESP-tool just by calling install ESP-tool. It downloads latest ESP-tool, and we're good to go. Second, I have this new shiny dev kit, which uses the ESP32C3 in it, and I've already connected to my computer with a USB cable, so that's good. And last, I just need to call ESP-tool.py, and the command I want to use, in my case, flash ID, which just tells me what kind of a flash memory do I have connected on my dev kit. Okay, we can see ESP-tool is running. It's giving me some output, and it gave me information about the flash chip. It's that easy. The second command to get some information out of the chip is read mac. Okay, next, ESP-tool allows me, and I think this is the most important part of ESP-tool.py, it allows me to manipulate flash memory contents. It allows me to write data, read data, or erase the flash memory data. So let's show an example of that. My dev kit at the moment is empty. It's raised, it's running nothing. And if I open my terminal, I can see I have some binaries which have been compiled by ESP IDF, and I want to write these binaries or upload these binaries to the ESP chip. So what do? I just call ESP tool, write flash, and then supply desired offsets and desired binaries. So what I just put in right now is that I want to flash bootloader.bin at 0, blink.bin at the second offset, and partition table at the third offset. And if I run the command, when it finishes, now it's writing the data, and when it finishes, we should see the ESP dev kit start to blink, because it's just a blink example. And we do. The LED is blinking, so the write has been successful. Beautiful. So that was writing data to the flash memory, but also I can read the data back, which is quite useful for making backups of your applications. When you want to upload a new program and you want to back up the old one, you just call read flash. Starting from address 0 size, you just input the size of your flash chip, for instance 2 megabytes or 4 megabytes, and the output file where you want to store your backup. And then you can use the erase flash to wipe the whole memory chip or just erase a certain region in the memory. Last but not least, ESP tool allows me to prepare binary executable images for flashing. This set of commands do not actually require a serial connection. That means I don't have to have a dev kit or ESP chip connected. Let's see an example. In my folder, I have some bin files, and I also have an ELF file, which can be flashed into the ESP chip memory. But I can use ESP tool, ELF to image, and I just point it to the blink file. And what's also important, I need to supply the C argument and tell it what chip do I want to create the image for. In my case, it's ESP32C3. And if I run the command, we can see ESP2 runs and creates an ESP32C3 image binary, which I can then flash into my chip. Okay, that's how you use ESP tool. This was a set of basic commands. There's more, but we're not going to get into that right now. I'm going to, in the next part of the presentation, explain how ESP tool works and how to debug some issues which come a lot when we get GitHub issues or feedback from our customers or our friends. We get a lot of feedback about problems with connecting and using ESP tool with real hardware. So I think it's quite beneficial to understand how ESP tool works and what it actually does under the hood. And this helps me to debug a lot of these issues. So in front of us, we can see a typical esptool.py output. I just showed you how to use it in terminal. We've seen this output, but let's dissect it a little bit. So when ESP tool runs, first it searches for a serial port. If it finds a suitable serial port, it tries to establish serial connection. So it starts connecting to the chip. And how does that work? It starts resetting the chip into a download mode and then sending synchronization packets. And if the synchronization is successful, it can then continue and talk to the ESP. If we can talk to the ESP, we can actually detect what kind of ESP are we using. That's why chip type auto detection is executed. And if ESP tool is successful and detects what kind of chip are we using, it can then do more. In the output, we get some information about the chip. This is a log using ESP32H2, which is an upcoming chip, and we get some information about it. Then ESP tool uploads something called the flasher stub and runs the stub. After the stub is running, our desired command is executed and we get the output. In this case, we were running the flash ID command, so we get the flash ID data. Okay, so let's go over these step by step. So what do we need in order for ESP-tool.py to work? The most important thing is working serial connection. As I showed you, most development boards can be just connected via with a USB cable, and that is because these boards are often equipped with a USB to UART bridge. This bridge translates USB signals into UART, which is then consumed by ESP32, and this allows us for a seamless experience. In the diagram, we can see that the development board is actually holding both ESP32 and the USB to UART bridge. But this doesn't always have to be the case. There can be cases where you don't have a dev kit or you're connected to a real device, such as this one. Here I have a ESP module, which doesn't have the USB to UART bridge. So for that, I have to use an external bridge like this one. This is the ESP proc, which is connected to the ESP chip. And the proc is then by a USB cable connected to the host computer. In the diagram, we can see that these two are actually separated into two units. We just have to make sure that the TX on the ESP chip is connected to the RX pin on the USB to UART bridge and vice versa in order for the serial connection to work. If we have this, we can actually change some of the parameters of the serial connection. We can choose a different port, or we can choose a different baud rate. When ESP-tool is starting to talk to the ESP chip itself, it always uses this baud rate. But when you're uploading or downloading data with write flash or read flash commands, you can actually use faster baud rates, which results in faster uploads and downloads. It's quite useful, but not all drivers might support this feature. So be cautious. If a faulty serial connection exists, you might often see an error like this one: failed to connect to Espressif device, no serial data received. What should we do in this case? Well, it's time for some debugging. And what I often do is that you're actually able to connect to the ESP chip with any serial terminal programs. If you don't know what that is, but for instance, use the Arduino framework, it's the serial window you can open, and this shows you the data which the ESP chip is sending into the host computer. There are many serial terminal programs. I like to use PySerial, which is a Python module, and it comes with ESP-tool. So if you install ESP-tool, you can also use this one just by running the command python/m serial.tools.miniterm and then giving it the port and desired baud rate. We can try that right now. And if we do that, and input the right port and press enter, you can actually see the data that is coming from the ESP chip. In this case, we can see the output is synchronized with the blinking LED. Okay, so if you see some sort of data coming to your screen, that means that the serial connection is working, and ESP-tool should be able to communicate with the chip. That's the first part of debugging, and it's important to determine whether you have a working serial connection. All right. Under that, you can see a bootlog example. We'll get to that in a minute. Second, and equally important part of working ESP-tool is that the chip has to be set into a download mode. So what is a download mode? When you reset your chip, it just starts executing the application that is loaded into the flash memory. But there's also another mode which allows you to download a new application, and the ESP chip enters this mode or bootloader, if you want to call it that way, only if the boot mode strapping pin is pulled low or bridged to ground on chip reset. The boot mode strapping pin is GPIO 0 on most chips or GPIO 9 on ESP32C3 or C2. If for some reason ESP2 fails to reset the chip into a download mode, you get this error message that the chip needs to be in download mode. This error message is only available on new chips. Old chips like ESP8266 don't have this feature. So if we see this error message, what do? Well, we have to debug a little. On most development boards, resetting into the download mode happens automatically because ESP2.py can assert the DTR and RTS control lines of the USB to UART converter, which is on the dev kit, or if you're using an external one. These DTR and RTS control lines are connected to the strapping and reset pins of the ESP. So the DTR line is connected to GPIO 0 or GPIO 9, and RTS is connected to enable pin. And ESP2 can then trigger these lines to reset the chip. But some dev kits, or if you're talking to a bare ESP, do not have this circuitry. What can I do in this case? Well, you can also turn the ESP chip into a download mode manually. And that is done by pressing the buttons of the dev kit. You can see most dev kits have two buttons, first and second. And to switch into the download mode, you just need to hold the boot button, which pulls the GPIO 0 low, and then click the reset button. Or if your dev kit doesn't have the buttons, you can use a wire or piece of metal to bridge GPIO 0 to ground and then reset the chip by connecting it to power. This basically does the same thing. If we switch back to our terminal, I can still see data coming out. And if I press the reset button, we should see some boot log and the application start over. So I'm going to press it now. And we see that the ESP boots and just loads the application again. I'm going to show it a few more times. Okay, but if I hold the boot button, this one, I'm holding it, and press the reset button right now, we can see that the ESP stopped blinking because the application doesn't run anymore, and it actually reset into the download mode, which is signified by the boot log and the waiting for download prompt. If you have these two things, working serial connection and you've been able to switch the ESP into download mode, ESP2 is good to go and ready to communicate with the chip. This behavior, this auto reset behavior, can actually be disabled just by supplying the before no reset argument to ESP2. This might be helpful in some cases or in production environment. So when ESP2 is able to talk to the chip and it detects successful download mode, it attempts to detect what kind of chip that is. And you can actually change this behavior by supplying the chip argument and telling it what kind of chip you are connecting. So if you call ESP2.py chip ESP32C3, the auto detection will be skipped and not attempted. Auto detection has two methods how to determine what kind of chip is ESP2 talking to. The second detection method has been added quite recently and works with the new chips. It has some benefits, but the old chips like ESP8266 don't support this detection method. So that's why sometimes you might see this message, unsupported detection protocol, switching and trying again. It's nothing to worry about. If ESP2 can actually detect the chip, it's all working just fine. All right, chip is detected. So what happens next? Well, the flasher stub is uploaded. What is the flasher stub, you're asking? So let's imagine the problem, or it's a real problem. When the ESP chips are manufactured, the ROM bootloader is burned into the ESP chip, and this means that the ROM bootloader cannot be updated ever again. New version of ROM bootloader is issued only when a new chip revision is released. So this means you can't really update the ROM bootloader or apply patches to it. That's why we have a solution called the flasher stub. ESP tool actually implements a flasher stub to temporarily substitute or extend the ROM. This flasher stub is uploaded to the RAM of the ESP chip and executed when connecting to the chip. And what happens next, that all following operations are then handled by the flasher stub instead of the ROM code. This behavior actually allows us to do some things and gain some benefits. First of them, we can use more heavily optimized UART routines. This brings us improved performance of some operations like writing and reading flash. And also, because of the flasher stub, we can actually patch any bugs in the ROM bootloader, and this allows us to react to the feedback from our community and customers and improve our products. If you have a use case where the stub loader is not needed or actually must be turned off, you can do that. To disable the stub loader, you just provide the no stub argument to ESP2 and call your command, and if you do that, all operations will then be handled by the ROM bootloader, which is burned into the ESP chip. When debugging ESP tool, you can actually trace the interactions between the ESP chip and the host device, your computer. If you supply the trace argument to esptool.py, you will see a summary or output of all the bytes that are going through the wire, through the USB cable to the ESP chip and back. This can be useful when debugging or when you're providing information for bug reports. So if you open a bug report at GitHub, chances are you will use the trace function to give us some more info about your problem. Okay, so that's how ESP2 works, and that was a little introduction to debugging the connection. I will now introduce other bundled tools because, as I said, ESP2 is a Swiss Army knife, a complete tool set, so there are more tools. There's ESP-Effuse.py and ESP-Secure.py. These tools are meant for production environments, and they are not really intended for hobbyists, and they can be destructive. I will talk about that in a minute, but just to summarize, it's not really meant for a basic user, but it can be beneficial to know how to use these tools. For instance, ESP-Effuse.py allows you to read or write or burn effuses in Espressif chips. So what are effuses? Effuses are one-time programmable bits which are actually in the ESP chip itself, and they can be burned only once. They can go from 0 to 1, but not back. So that's why it's quite possible to permanently damage or brick your ESP device if you burn effuses that you shouldn't have burned. So that's why we say to use the tool with great care and only if you know what you are doing. But there's one command which actually is not destructive, which might be quite beneficial for the normal user. It's ESP-Effuse.py summary. And this allows you to get some useful information about the chips, such as factory MAC address, silicon revision, analog to digital calibration, converter calibration data, and active security features. Let's see that in action. So if we will call ESP-Effuse.py, tell it on which port our ESP chip is, and then call the summary command, you can see the effuses in the chip and a summary of these. For instance, you can see the MAC address right here. If you want to also try other commands like burning effuses and such, and you don't want to destroy your ESP, you can use a virtual mode. virtual mode is enabled by supplying the vert flag, and you also need to specify the chip, and this will then create a virtual file which acts like the real eFuses in a real hardware, and you can perform some operations on this file, and then you can just delete it if you're done trying your commands. It's a safe way to try ESP-fuse.py. The next tool is ESP-secure.py. It's a tool for manipulating secure boot and flash encryption data. More about this tool can be found in the ESP-IDF documentation, which can be found on this link, docs.espressif.com, projects, ESP-IDF. And then if you go to API guides, you can read about secure boot and flash encryption. This was just scratching the surface of what ESP-tool.py can do for you. It can do much more. So you can just run ESP-tool.py/h, like help, or visit the online documentation to learn at docs.espressif.com/project/ESP-tool. There's a lot to learn, and it gives you great power when you know what to do. We are continuously developing ESP-tool.py, and we are gaining feedback from the community and trying to improve the tool every day. So, for instance, we just recently launched new documentation, improved stability and diagnostic messages to be more user-friendly, and added ability to flash chips over USB-C/DC, and there's much more what we've done in the past few months. But also we have plans for the future, such as we want to refactor ESP-tool to be more usable as a Python module for implementing as a part of other Python projects. We are also planning support for new chips, and we want to implement your idea. So if you have any ideas, feel free to send a feature request, or you can contribute in other ways. Contributions are always welcome. You can report an issue, or send a feature request, or even better, you can fix a bug, add a feature, or write documentation. If you do that, it will be more than welcome, because ESP-tool is started as a community project, and it still is open source community project. So these contributions are very welcome. To learn about contributing and development mode installation of ESP-tool, you can just go to ESP-tool docs and go to the contribute article. There you can find everything you need to start developing ESP-tool or fixing bugs. Okay, that was it. I'm glad this talk actually helped you to understand how ESP-tool works, what it can do for you, and that I was able to give you some insight under the hood of ESP-tool. Thanks for listening and joining me today. Have a nice day. And if you have any questions, feel free to ask.